siguiente panel es del Colegio Técnico Ingolstadt de la ciudad de Ingolstadt, Universidad de Alemania. Modera Juan Pablo Supervisor en Volkswagen, Argentina, presidente del Departamento de Educación y Formación Profesional en la UIA. Y disertará Daniel Grossmann, profesor del Colegio Técnico Ingolstadt de Alemania.
Voy a dar el lugar al profesor doctor Daniel Grossmann, que en resumen es un especialista en el Industria 4.0. Él ya ha participado anteriormente en el Congreso, pero es un experto en el tema. Hello, Daniel. Please go ahead with the presentation.
Thank you very much. I hope you can hear me well. So let me just go and share my screen. Okay, here we go. So let me just start the presentation. All right, so now you should see my presentation, I hope. So
yes.
Very good. So let me send a warm welcome to all of you participating in the Industry 4.0 Congress. I'm very happy to give a presentation on the topic that you can see here. As already introduced, my name is Daniel Grossmann, and I'm doing research at the Technische Hochschule Ingolstadt in the area of Industry 4.0, and here specifically in the area of information modeling. And what this means, I hope to bring to you in the next 20 minutes. So the topic of my presentation is AutoX, semantics-based automated data engineering. And let me start with a slide to introduce the topic of data engineering. So what you can see here is a drawing that shows the three important pillars of data engineering. And the first one is extracting data. So we need to extract data from devices, for example, so that we can then in the next step transform the data, so that we have the data available in a format that is useful to us, so that then in the last step we can load it into some storage infrastructure, so that we then can go ahead with what we want to intend to do initially. And what we intend to do, that is could be an Industry 4.0 application, like for example a predictive maintenance application. But before this application can run, we need to extract data from the relevant devices, transform and load this data. So with that being said, when you look at some of the slides about Industry 4.0, this step of data engineering always looks very simple, because in a lot of slides and presentations, you will just see that somehow the data is coming from the shop floor devices into the cloud, and then in the cloud we can have our Industry 4.0 application. So the data is just seamlessly flowing into the cloud for further processing. Well, in reality, it looks a bit different, and I'm sure that some of you know that part of reality quite well, because when we look into industry and industrial production processes, then we deal with machines coming from different vendors, components coming from different vendors, controllers such as PLCs coming from different vendors. So it's multi-vendor everywhere, and the data from these machines and from the shop floor now somehow needs to find its way into the Industry 4.0 application for further processing. So the problem with that is that today, as many of you know for sure, all these vendors have different communication protocols, different data structures. So it's showing by these different symbols of plugs here, we cannot just seamlessly connect them into Industry 4.0, but we need to do data engineering. So that means we need to build software to extract, transform, and load the data. And this software sometimes looks a bit shaky. So we implement some data adapters, drawing data from devices, transforming them, but it's not very, or quite often it's not very robust software. So I like to always to show this picture because this symbolizes the type of data connection that we have between the machines and our Industry 4.0 applications. So well, this can be done and it will work. So we can go ahead and bring the data from the components up into an Industry 4.0 application and then go ahead and process it. But this has some drawbacks, and I would like to bring up an example from the chemical industry here. And here in the background, you see a chemical plant. And within such a chemical plant, a very common asset or very common piece of equipment is a pump. So here we see a pump that might sit here in the chemical plant, and the pump is a very interesting piece of equipment because it is rotating, and whenever things rotate, they're gonna degrade and there is wear, so there might be vibrations coming at some point in time. So this pump will degrade over time, and the idea is to monitor that pump so that we can see that it's degrading, and we can predict when it will fail and then do some maintenance before it eventually fails. So this is the use case. It's a very straightforward use case. And so if we want to solve that use case, what is the typical approach today? Well, today a data engineer goes ahead and gets the plant structure. So this is an example of a part of a plant structure, a very small part of a plant structure of a chemical plant. It's the so-called piping and instrumentation diagram. And the data engineer goes ahead and reads this diagram, and he interprets the symbols that he's seeing, and with that he can understand the content of this diagram. And with the pump monitoring in mind, the data engineer would now look at this plant structure and search for pumps, and then he would see by this symbol here that here we have a pump, and the pump needs a drive. So here we have the drive that is bringing the rotation into the pump, and also the data engineer sees and understands here is a pressure measurement measuring the pressure on the outgoing side of the pump. So by reading, interpreting, and understanding, knowledge is created in the mind of the data engineer, and with that knowledge in mind, the data engineer can now go ahead and implement this pump monitoring scenario for this pump here. So what would he or she do? First of all, you need to find the frequency inverter for the motor and the pressure transmitter in the automation system. So you need to find which frequency inverter you need to get the data from and which pressure transmitter you need to get the data from. And then you can get the data and bring it into your pump monitoring and optimization application. But although the arrow is very simple, there's a lot more to it in reality, because we need to go ahead and implement our data adapters. So we need to do manual data engineering. That means extracting data from the devices using different communication protocols. Then transforming the data, because they have different data types, the data structures are different. So we need to transform them. And once we have done this, then we can load the data into our probably cloud-based monitoring and optimization application. So, and the task of the data engineer is first to get the knowledge how to do this, and then to implement it, to test it, and this may be the biggest pain of all, to maintain it over time. And this can be done, no question. And so now we have the pump monitoring up and running for this pump in our chemical plant. But chemical plants tend to be quite big installations. So the problem is there is not this single pump, but there may be hundreds of pumps in this chemical plant. And now the question is whether it's a good and useful way to go ahead, like with this manual data engineering, because what happens is doing all these steps manually is a lot of effort. A lot of effort equals a lot of time, and a lot of time equals a lot of money. So in the end, doing all this manually, it's questionable whether there will ever be a return on invest, and whether monitoring all these pumps really pays off, or whether it would be the better strategy to just let the pumps run until they die, and then to get a new pump into the plant. This is, of course, a question of criticality. For very critical rotating equipment, this makes sense, but for not so critical rotating equipment, it could easily be that implementing and maintaining these data pipelines is more expensive than just not monitoring the asset, not monitoring the pump. So maybe there is a better way to do this, and this is where I want to emphasize that what we need really is information. So data is fine, but data needs to be extracted, transformed, and so on. What we need is information, because information is knowledge, and I can use that knowledge to plan actions so that I can reach a defined goal. So if I just have data, in an example, 15 and 20, I have no idea what this data means, so I cannot draw any conclusion from it. But if I provide semantics to the data, and I know 15 is the number of minutes that I'm already presenting, and 50 is the number of minutes that I have in total for this presentation, then I can use this knowledge to plan actions to reach a goal. And in my case, it could mean the action is I better hurry up if I want to be if I want to finish in time. And this is the whole idea of information, knowledge that I can act upon. And this is why we need to go away from what we have today, which is data, and then manually working with the data, to information, because information is data plus the semantics. And this is the important point, now allows machines to understand the meaning of the data. So a machine can now understand what the data means and how it could use the data. So information can be understood by the reader, not only a human reader, but a machine as well. And so that means the meaning is known, and this means we get knowledge that we can use to take action to reach goals. And the interesting thing is that this understanding then happens at runtime based on a common dictionary, a common Industry 4.0 language, instead of, as it is today, that the understanding happens because programmers implemented it into different programs during the engineering phase. So it makes the whole system a lot more flexible. So information exchange is one of the strong foundations of Industry 4.0, and the means to do this is to use information models, because they define both the data content but also the meaning of that data. So let's go ahead and again look at this very same example, but this time let's look at how this would look like if we use information and the meaning, the semantics, and thereby go from manual to automated data engineering. So again, we have the plant structure, but this time the plant structure is provided in form of a well-defined information model, and now a computer can go ahead and read this information model and understand the content of this information model. So now we don't no longer need the step of interpreting what you read, but the information model can be directly understood by a machine, by a computer. So the computer can now directly recognize here is a pump, and there is a motor driving the pump, and there's a pressure measurement at the pump, and I can use that these two automation devices to get the pump monitoring up and running.
We have not a lot of time. Could you please round the final idea, Daniel?
Come again?
If you could close the presentation with the more important conclusions.
Okay, all right. I will go ahead, try to make up some time. So by reading that and understanding that, the computer can go ahead and do that trick that was done by the data engineer manually automatically. And the good thing by setting up this pipeline using configuration and deployment in an automated way, that can be done by a computer in a matter of seconds for hundreds of pumps at the same time. So now if we look at the plant with a lot of pumps, all of a sudden effort is no problem, time is no problem, and also therefore not money, because it's all automatic. And now the return on invest is clear because a computer is doing the costly part of the job. So let me just conclude. We need to go from manual data engineering, where we set up these data connections manually, to automated data engineering, where we use information models and standardized information models to connect our production assets to Industry 4.0 applications, because otherwise the manual effort is just way too high and the return on invest is not really available. So coming to the end, in Industry 4.0, I can often see projects that fail because connecting and getting the data from the machines is either a big and enormous effort. Information models reduce that effort. They define the structure and the semantics of the data, and this can be used to automate tasks that otherwise would require human interpretation. And with that, information models are essential to Industry 4.0, and information models with the semantics that they provide are the basis for future automated data engineering. So they are the basis for Auto X, for Auto anything. So with that being said, thank you very much for your attention. I'm happy to answer any questions if you have. Thanks for listening, and any questions, I'm happy to answer them. Thanks a lot.
Thank you, Daniel. Fue un resumen de la presentación rápidamente. Es decir, es importante no solo la conexión en Industria 4.0, hay que ver los protocolos, ¿no? Es decir, cómo adaptar eso y que tenga sentido para poder trabajar con la información. Es decir, los datos en sí no son información para la toma de decisiones en este caso, ¿no? Es decir, la complejidad de todos los dispositivos a conectar puede ser que hagan este trabajo infinito. Entonces, por eso el uso de la información para que sea usada en forma acorde, ¿no? Y adecuada. Eso hace que el retorno de la inversión sea lógico y podamos tener conectado las variables relevantes de la industria que quiero automatizar. ¿Alguna consulta, alguna duda que quieran?
Muchas gracias, Juan Pablo Dri, supervisor en Volkswagen Argentina, y a Daniel Grossmann, profesor de...
Agradecemos a todos.
Sí.
Thank you, Professor Daniel Grossmann, to the presentation and for the University also.
Thank you very much, and wishing you a great day. Bye.
Gracias a todos.